Hello everybody, this is Farhad and we're going to cover Lab 10 today. And this week, quite fittingly, we are covering disease spread and how looking at differential equations that describe the way diseases and epidemics in particular spread among populations. Um, and I feel like studying this can give us all a good perspective or a good understanding of what's currently happening in the world with respect to the coronavirus. All right, so the model that we're looking at is called the SIR model, where S is the number, S stands for susceptible, people who don't have the disease yet but could get it. I is the number of people who are infected who currently have the disease, and R is the number of people who have recovered. In the lab manual, it says that the disease is rarely fatal, and so we just take R to be the number of people who recovered. But you can also take R as removed, so they either recovered or uh, they've passed away, and so they're removed from this population of SNI. And so you can just consider them as a separate thing. You can take it as recovered or removed, and if you take it as removed, you can apply this model to diseases that do have a significant fatality rate. But anyways, before we get into what the lab says about these equations, I just want to note that I've left two links to YouTube videos in the description. One of them uses this SIR model in a with really nice animations and kind of runs a bunch of different simulations, looking at the model in depth and looking at different situations like of people traveling from one community to the other uh, and various other situations like that. And I feel like watching the video will give you a really good mathematical sense of uh, what's happening with COVID-19 right now and how it's currently spreading and what we can do and what we should do to slow its spread. So, and I also left on the second link is just about exponential growth, specifically looking at COVID-19 again and trying to make sense of the kind of numbers we're seeing on the news every day about the number of cases just jumping by thousands, and it kind of looks at exponential growth in the context of disease spread. So both those, I recommend those videos. They're really good, and I think it's good for all of us to have an idea of what's happening right now. Anyways, so let's try understanding these differential equations. So ds by dt is the rate at which the number of susceptible in the population changes, and again, a positive rate means the susceptible are increasing, a negative ds by dt means the population is decreasing. And we see that it's negatively proportional. A is just a proportionality constant. We see it's negatively proportional to s times I. This is the product of s and I. And what it's trying to capture there is like the interactions between people who are susceptible and people who are infected. So if you increase s, it's more likely that a susceptible person will meet an infected person. If you increase I, the same is true. And so S times I is kind of trying to capture the interactions between how much are susceptible and infected people interacting. And the more they interact, the more people get infected, and therefore the number of people who are susceptible decrease. And so we have a negative rate of change. So that means a decrease for the number of susceptible people. That's the first differential equation. The second differential equation looks at the rate of change of the infected, and here it's the exact same thing but positive for ASI. So it's here A is the same proportionality constant and S times I interactions. The more interactions there are between susceptible and infected, the more people get infected. Therefore, uh, it'll have a positive impact on the rate of change of the infected. And we also have this negative BI term, and that's because the more people who are infected, the less susceptible people there are, and so the less chance it is for you to um, infect someone else. If like imagine a situation where everyone's infected, uh, and then in that situation, there's no way that you're going to infect more people, and so that's why we have this: the more infected there are, the rate at which more people get infected decreases, and so that's why we have this negative BI term over here. And the recovered is a really simple one. It's just proportional to the number of infected. The more infected people are, the more likely they are to recover or be removed, uh, as I said. And so this is the model we're going to look at, and we're going to assume one critical assumption. which is reasonable is that we're going to assume over the period of time we're looking at, which is going to be 4 months, that the population doesn't increase, or it remains reasonably constant, that there's no large boom in population or anything like that. So we're going to assume that the population stays at 5 million throughout the lab, um, and we go from there. And so since we know the population is going to be constant, we can just we don't have to look at this third differential equation over here, because we can just, if we know S and I, we can just calculate R, because we know the total will be 5 million. So we can just if we know S and I, the remaining 5 minus that will be R. So we can just ignore this equation over here and focus on these two and study this system of equations. All right. I'll get into the questions now. I feel like this lab is relatively easy to do, and I'll try going over it pretty quickly. So the first question gives us specific values for those proportionality constants. I just want to note, since we are currently going through an epidemic, these proportionality constants depend on various things like the probability of, say, if an infected person and a susceptible person sit together, what's the probability of uh, the disease passing from one person to the other, and these constants are affected by things like how is social distancing being practiced, are people doing the right things with respect to hygiene, are they washing their hands, are they, all these sorts of factors go into these proportionality constants here. And so that's just a note in relation to um, where these come from. And if you watch those videos I linked, you'll kind of see more of the different effects various actions we can take, like social distancing and hygiene and things like that, can have on how what effect it can have on the rate of increase and decrease of the susceptible and infected. So question A asks us to plot this in p-plane. So for part A, just use these values of 1.1, 1.3 and plot it in p-plane and submit a graph of S versus I. And again, for this question, I really recommend looking at the grading rubrics. It tells you which graphs you need exactly for which question. So plot S versus I, and you need to do it only for the specified computation interval over here, from t equals 0 to t equals 4. So over here, t is in months. So we're just looking at it from 0 to 4 months. And we start at the number of susceptible being 3 million and the number of infected being 1 million. And so that's going to be our initial condition. We're going to look at it for 4 months. So plot for first part A, you just need to submit like the initial p-plane orbit you get, S versus I. And then you also need to submit a plot of S against time and I against time, and just describe what the pattern is. What is really happening to these populations? Just a word. Is it increasing, then decreasing, or does it have a max? Uh, just a sort of a general description. And so you need to submit those two separate graphs. Part B asks what's the max number of infected and when does it happen? Again, you can just look at the graph again. So this graph, the graph I have on the left over here, it's an example of the graphs given by p-plane when you plot against time. But here I have two graphs. On yours for this thing you'll have one, and you see this black line over here. So if you go to your p-plane, you'll see a black line like this. If you click, like suppose I want to zoom into this area over here, if I put the black line over here and I click here, and then I'll have another black line and I move it over towards the right and I click there, you'll see that the black line sticks there, and then you can click crop, which will be somewhere over here, and then you'll be able to zoom in. And then when you want, you can click restore and you can come back out. That's how you zoom in these plots. So you can zoom in to find, okay, what's the max number of infected people and what time does it happen at. Part C, you'll have to use this plot that I have here. So here's a plot of susceptible and infected together on the same plot. And so is S ever equal to I? So you'll have to look at this and see, is there ever a time when S is equal to I? And note that it's not, may not be just one time, it could be more. And you need to give the times at which they're both equal. So make sure you look at the grading rubrics. It wants a plot of S against time, then I against time, and then both against time. So it's kind of, I guess, not fully necessary. You're doing the same thing again, but that's just what it wants. Anyways, part D just asks you to estimate a few values from the graph, like at time equals 2 months in, what is the value of S, what is the value of I, and then at time equals 3 months in, what is the value of I again. All right, question 2. So we have a situation where the virus mutates at t equals 2. So that's 2 months after we first started looking at virus. And we see that A reduces to 0.5 and B stays the same. So this is going to have some impact on the way the virus is going to spread. And so what we want to do is see how much of an impact it has and what kind of impact it has. So we estimate the number of infected 1 month after the mutation. And so remember, this is that we start at t equals 2. So to do this, you need to choose your initial conditions to be what you found in part D of the previous question. We saw that we found S and I at t equals 2, so use those as your initial conditions uh, with this new A value over here, and then find out what I of 1 is in that situation and compare to what I of 3 is from the previous situation, because here we're starting from t equals 2, and in that situation we started at t equals 0. And so that therefore we're comparing them both at 3 months after the initial start. So make sure you just put in the right t values and you make sure you look at the right place. Then just compare it with I3 from before and explain what effect the mutation had. All right, so for question 3, it asks you to fill in these two tables on the right hand side. And basically what the tables are, the difference between the two tables is the A value. And each row represents a different initial condition. So for the first row over here, it's 3, 2, then 3, 1.1, 3, 0.5, 2, 3. So you'll have to enter different initial conditions. And what it wants you to find for each different initial condition and different A value is what is the number of susceptible people at time equals T star, where T star is the time at which the number of infected is at a max. So not the number of susceptible. So what is the value of the susceptible at the time when the infected is at a max? So when the most number of people are infected, how many people are susceptible? So that's what it wants you to find. So you just plot each one. You enter A equals 1.5, B equals 3. You put a specific initial condition in, and then you find out where the maximum infected is, and look at that same time how many susceptible are there, and then you enter it into the table. And try doing it as precise as possible. And when you do it, you'll notice that the number of susceptible when the infection is at its max will be B by A. And so we want to explain why that is. And the clue over here is look at this equation. And when the infection is at a max, when the number of infected is at a max, what does it tell you about this equation? And then you can solve from there to figure out why S equals B by A. And then put one comment on whether or not in your table you found this to be the case or you did not find this to be the case, and how close was it actually to B by A. But make sure that you actually calculate it in p-plane for all the different initial values and the two different values of A. Question 4 to me is probably the most interesting question because it kind of asks about real life scenarios and how you can use these differential equations to answer practical questions that one would want to know about how a disease spreads and what concerns there are. So it first tells us about a variable change that is kind of useful. So we express with small s, small I, and small r. We write the number susceptible as a fraction of the total population, and the number of infected as a fraction of the total population. And so given this variable change, it's useful. You'll see why as you read the question. So what is small s plus small I plus small r, given that we use this variable change, and what we know about the relationship between s, I, and r and n. So what would small s plus small I plus small r equal to? You need to answer that even though it's not like part A or anything like that. Make sure you answer it. The next part of the question asks you to derive the new system of equations with these new variables. And so we have this old system over here. And what we want to do is change the variables to the small s, small I, small r instead of these large big S, big I, big R, capital. And the way to do that is the chain rule. And I put down an example over here. So ds by dt with the small s is ds by ds, small over large, times ds by dt with the large s. And so you can see how that would cancel out, and you did get small s, ds by dt with the small s over there. And so to get the first expression, you look at this equation over here. And so you have a small s in terms of large S, so you just differentiate to get small s, d small s over d large S. And this we have from this equation over here. And so you can just plug that in directly. And in your answers, you should plug in n equals 5 because the total population is 5 million. And so just to simplify it and not have an extra constant there, you can just put in 5 because we know n equals 5. And so then you get 3 new differential equations from this. So make sure that you do this right. If you have trouble doing this, just send me an email or something like that, because you won't be able to do the rest of the questions. Or it'll be harder to do the rest of the questions if you don't do this variable change. Part B, this is the interesting part where it asks you to say, it gives you 3 different statements and asks you to investigate whether or not these statements are true or false. And so you should read the question. I won't give out too many details about it, but you should read the 3 different statements. And what you need to do is first answer statement 1. Is it true or false? So you say you think it's false. So you say false. And you need to explain why you think it's false. So you need to plot. You should need to show your plots. For all of them, you need to show plots. Again, check the grading rubrics. You need to show your plot, and you need to justify why you said true or false based on what you see on the plot. Say in the plot you can see that this happens, so that's why the statement is true, or that's why the statement is false. And for each statement you'll have like a different initial condition and a different thing you're looking for. So yeah, that's why I think this question is nice. You need to convert these words into like the values for the variables. So half the population being susceptible, what does it mean in terms of our variables? So what initial condition would you give? If suppose it says initially that half the population is susceptible, you need to, using that, you need to choose an initial condition for small s, and then other information because you need to choose an initial condition for small I. And again, you won't be using the third equation, you'll just be using the first 2 of your new derived equations, but you have to derive all 3. Yeah, that's it for question 4. Again, if you have trouble converting this or trying to convert the words into like the initial values that you need to use and stuff, just shoot me an email. And the last question is purely mathematical, and the first part asks you to show this equation. And again, you just use the chain rule. We have ds by dt and di by dt. Use those together, and you'll be able to find what ds by di is. The second part, slightly more complicated. It asks you to solve the differential equation, and it gives you the initial conditions of just I0 and S0. And you want to show that you want to solve it for I of t. And you'll see that it is a separable equation, and so I won't say too much on it, but you can separate it, integrate both sides, plug in the initial conditions, find out what the value of c is in terms of I0 and S0, and then you should get this as your answer. Again, if you have trouble with it, just shoot me an email. So that's it for this lab. It's pretty short. Hopefully, it doesn't cause too much of a headache. Again, you can use the discussion board on Blackboard for questions, and I uploaded the grades for Lab 7. The grades for Lab 8 should be up soon too. You can email me with any questions regarding the grading you have. If you think you lost points when you shouldn't have, just shoot me an email. I'm happy to change your grade in case I made a mistake. And as I said, the links in the description are really good. There's some really nice animation and explanations, and I recommend checking them out if you have the time, and perhaps even sharing them with your friends or family. All right, that's it for this week. I hope all of you are doing well. If you have questions, send me an email, and I'll upload another video next week. Bye bye.